Hello, and welcome to this 7th lesson in this series on Lagrangians and Hamiltonians. In this lesson, we'll be looking at plotting trajectories in phase space and an associated theorem called Liouville's theorem. I've almost definitely mispronounced the French there. Now, why is this useful? So this is really useful for trying to get information from really complicated systems that have lots of particles or where the system isn't solvable analytically. So on the left here is an excellent book called Nonlinear Dynamics and Chaos, and this whole book is about how to get information from complicated equations of motion that you can't solve, but by plotting things in phase space, you can get some information out and you can kind of get some understanding of the dynamics of the system. And on the right is a diagram from one of my papers where, again, we couldn't solve the system analytically, but by plotting every single particle in the system in phase space, we can start to get an understanding of how the system is evolving in a way that we couldn't do just from the equations. Before we move on to phase space, we're going to look at something called configuration space. And configuration space is essentially just the space of all possible generalized coordinates. So when we were using Lagrangian mechanics, all the possible values of Q, what that defines configuration space. Okay, that's probably quite abstract, and to really see what the configuration space is would require a much higher level of maths than we're going through in this course. But let's have a look at a couple of examples just to kind of get the idea. So what is the configuration space for a point particle moving in 3D? Well, if it's moving in 3D, it's got three different coordinates, x, y, and z. All three of them can take on any value. So the configuration space is r cubed. Then for B, what is the configuration space for a pendulum moving in a single plane? So just the pendulums we've seen that swing back and forth. So the configuration space for the pendulum is just a circle, because the end of the pendulum can go in a circle. And then finally, this is a bit of a challenge. So a pendulum with a pin at the top, so it stops it going all the way around. It can only swing from the top and back again. It can't go right the way round. So the configuration space for this is a line segment that goes from minus pi to pi. Because our coordinate can only go from minus pi to pi, it's just a section of the real line. And this shows us that it's not the geometry that matters. What matters is just the values the coordinates can take. But we're not going to spend any more time on this. It's quite a mathematical and geometric idea, and if you want to take classical mechanics into higher levels of mathematical physics, you'll see more of this. But for now, that's all we're going to see. Okay, so we can now look at phase space. So phase space is the space of all possible values of the coordinates and the momentum, and this is all combined into one. So the set of possible coordinates, that's just the configuration space. And the momentum part, because that can take any value, momentum is just a real number. There's no extra geometry or topology like we saw with the pendulum being a circle. There's none of that extra stuff. And if we take a point in phase space, and a point in phase space is just given by the coordinate and the momentum, this point uniquely characterizes the system. So once we fix the point, we know exactly how it's going to evolve. Now this is different from configuration space. In configuration space, we just saw where the system is. In order to know how it's going to evolve, we would also need the velocities. However, now, because phase space includes position and momentum, a single point tells us everything we need to know. Now, where this becomes useful is that we can plot trajectories in phase space. So if we just assume a particle moving in one dimension, it's got some Hamiltonian. For the moment, we don't care what it is. So we have our set of coordinates, as one axis, our set of momentum as the other axis, and then we can plot our trajectory on this in the same way we would plot kind of any other graph. So this line here represents how the system evolves over time. Okay, that's all well and good if we want to plot just one or two different trajectories. But we can find a way to characterize all trajectories through phase space. And we can do that by defining a vector field that has components q dot, p dot. So this vector field, defined everywhere on phase space, is a little arrow that tells us how the system is going to evolve over the next small interval of time. So q dot, p dot points in the direction the particle is going to travel in phase space. And this is just given through Hamilton's equations, through the equation of motion. So we can plot this vector field everywhere, and the arrows tell us how the system is going to evolve. Okay, so let's see an example of this. So let's sketch what's called the phase portrait for a free particle with this Hamiltonian. And I haven't said what a phase portrait is yet. A phase portrait is just the vector field and a couple of useful or standard trajectories drawn on top. So in order to sketch this, firstly we need to have our phase space, and I've included a grid there just to make sketching a bit easier. And then we need to calculate our vector field. So our vector field, q dot p dot, is given by Hamilton's equations. Then this is given by p over m 0. We just do the derivatives. So now we can start plotting it. So if we look at the origin, p is 0, q is 0, and so the vector is just 0, 0. As we go up the p-axis, q is 0, but as p increases, q dot increases linearly. And similarly, as we go to the negative q part of the graph, it's exactly the same, just reflected. And then because this vector field doesn't depend on q, as we increase q and decrease q, it's exactly the same. Now let's plot a couple of example trajectories. So here's one, and because all the red arrows are pointing to the right, this trajectory just follows those, and it travels to the right. So this means if we start our particle at the tail of this arrow, so we have negative, or q is -3, whatever -3 is on this axis, and it starts off with a small amount of positive momentum, the momentum's not going to change, and the particle's going to travel in the positive q direction. And we can plot another trajectory. So this trajectory is saying if the particle started at positive 4q, positive 3q, and it had negative momentum, it's just going to travel to the left. And here, because the arrows in the vector field are bigger, it's going to be traveling faster to the left than the trajectory up on top. For our second example, this is a particle in a harmonic potential or a quadratic potential. I think you've seen this before, but I've taken out all the constants just to make it easier to plot. So have a go plotting the phase portrait for this on your own, and then I'll go through the solution. Okay, so now you've had a go on your own. In order to solve this, the first thing we need is to work out the vector field. So the vector field is given by p minus q. So now we can start plotting this. If we start from q equals 0, we see that as p increases, the vector gets longer. And then similarly, we can keep p as 0 and see what happens is we just change q. And then we can go along the 45 degrees. And what we see is, maybe as we might expect, all of the arrows, they kind of make a circle. And we can plot a rough trajectory like this. So we can interpret this by saying that, let's say we start our trajectory, we start our particle at q equals 2 units, and it's got no momentum. And so, in that case, the particle rolls down the hill, or whatever is causing the potential. Let's say it's a hill, so it rolls down the hill, so momentum gets more and more negative. At the bottom of the hill, it's got its maximally negative momentum. It starts to go up the other side, and as it goes up the other side, momentum decreases. As q increases, it gets to its maximum, and then it starts to roll back down the other way. We are now going to look at Liouville's theorem. So what this states is that the volume of any region in phase space is invariant under Hamiltonian evolution. So that phrase, Hamiltonian evolution, all that means is our system obeys the equations of motion we've seen so far, and we derive them from the Hamiltonian. That's all that means. So what does this theorem mean? So if we have our phase space, and let's say at some initial time we measure the coordinates and momentum of our particle, well, we're never going to know this exactly. So it could be somewhere within that region, or there's some probability distribution, but we know that the particle is somewhere within that circle. We know q is roughly in the centre of that, and its momentum is roughly in the centre. But there's some uncertainty. Now, over time, that evolves, and that probability distribution will spread out and move. But the volume of it never changes. So you see here that even though it's got wider in one direction, so we might have more uncertainty in one direction, that's compensated for less uncertainty in another direction. And finally, because this is invariant under Hamiltonian evolution, means that the system needs a Hamiltonian, so something like friction doesn't count. So let's go through the proof of this theorem. Because this is quite a visual proof, I'm going to go through it in the video instead of writing it into your booklet. So initially, the particle is in this region R of phase space, and we can work out the volume by integrating dp dq over this region, and where dp dq is some volume element in phase space. Now, sometime later, it's in this region R tilde, and the volume element is dp tilde dq tilde. And we can work out the new volume by integrating this over the new region. Now, in order to relate the two coordinates, we can write one in terms of the other. So we know that q evolves to q tilde. And we can expand this in terms of the time, so dt, and we're just going to expand to first order. So q tilde is equal to q plus dq by dt dt plus higher order terms that we're going to ignore. And we can rewrite dq by dt using Hamilton's equations. And then, similarly, we can rewrite p in the same way in terms of Hamilton's equations. Okay, so we can now begin to calculate the volume of the second region. So we have our integral, and we can rewrite this in terms of our original coordinates. So there's a few parts to this. Firstly, we have the determinant of the Jacobian, and that's expected from normal transformations of coordinates in integrals. However, what might be surprising is the integration over r, not r tilde. There's not a typo. That's because our coordinates, dp, dq, all come from that original region. So the values of p and q we're integrating over are just those in the original region, and they evolve to become the new region. So when we just look at those pq coordinates, they all come from r, so we're still integrating over r. So really, everything is down to the Jacobian. If that's equal to 1, then our volumes are the same. So let's calculate the Jacobian. So the Jacobian is given by the determinant of this set of partial derivatives, and we can substitute in our expressions for q tilde and p tilde above. Then, if we take the determinant, and I'm going to leave this to you, but it is just algebra, it does all cancel nicely, this is just equal to 1. And so we have proved Liouville's theorem. So, in summary, We saw configuration space is the space of all possible generalized coordinates, and phase space is the extension of this to include the conjugate momenta as well. And finally, we saw Liouville's theorem, which is that the volume of any region in phase space is invariant under Hamiltonian evolution.